Thank you all for coming, by the way. It's a great pleasure to be here. So yeah, as you heard, my name is Emilio Martinez-Paneda. I'm a senior lecturer in mechanics and materials at Imperial College London. And today I want to talk about how, by combining these two ideas of these two features of multiphysics and phase field modeling, we're able to mechanistically predict challenging material phenomena. And what I mean here by mechanistically predict is that we can finally explicitly resolve the underlying physical processes that govern this material degradation phenomena. So we can deliver physically based predictions. And I will show this focusing on three case studies or three areas that I find particularly exciting as a scientist, but that are also quite important from a technological perspective, right? Because they're critical for the energy transition. So this is hydrogen embrittlement, lithium-ion battery degradation, and localized corrosion. But before I start, let me emphasize that this work that I'm about to present is a collective effort. So all the merit goes to PhD students and postdocs of my research group and to our collaborators at Imperial and elsewhere. I listed some of them in the slide, but there's many others as well. So also I should probably say a few words about these two modeling paradigms that we have exploited quite a lot, multiphysics modeling and phase field modeling, because they are common to all these three areas that I will be going deep into it in a few minutes. So of course, multiphysics modeling, as the name says, is nothing but the coupled simulation of multiple physical phenomena. And I think that we know well what are the differential equations that describe thermal processes, mechanical processes, chemical processes, electrical processes. So the challenges here are in the coupling, so in their interactions, how do you define those interactions, and also in relation to the solution of this large-scale complex problem or very large time and space scale. So we need to come up with robust and efficient computational procedures that allows us to handle these large-scale systems. In regards to the phase field, the key idea is that phase field modeling, or many of these material degradation phenomena are actually interfacial problems. So they require the simulation of the capturing how an evolving interface moves, and this is, from a computational perspective, quite challenging because it's quite difficult to capture how an interface evolves, how a boundary evolves, how a boundary interacts with other boundaries, and how you have boundary conditions on top of that. So the phase field basically is a way of working around those challenges. So it's another way of formulating this interface paradigm that allows you to computationally work around those challenges. So whenever you have two phases, like here, you could think of the interface between these phases as a sharp discontinuous interface, so this will be the traditional idea, or as proposed by this phase field paradigm, you could smear the interface over a finite domain, and then use an auxiliary variable, this phase field variable, to describe where the interface lies. So this phase field variable will have two distinct values in each of the phases, so it will be 0 in the blue phase, 1 in the red phase, and then it will vary smoothly in between. And just by defining a differential equation that describes how this phase field evolves, then you're able to capture interfacial problems of arbitrary complexity. So it's a very simple concept, but it's actually quite a compelling one from a computational perspective. And there's multiple advantages associated with it. Three that I always like to emphasize is that the interface equation is defined in the entire domain, so there's no need for any special treatment. Second is that topological changes such as divisions or merging of interfaces can be naturally captured without any ad hoc criteria. And the third one is that it's very well suited for multiphysics problems because this interface equation can be very easily coupled with equations describing other physical phenomena. So this is something that we're going to explore quite a lot. And phase field modeling has been a revolution in many areas of science and engineering. So all started in the condensed matter physics community, where phase field is by far the most widely used tool nowadays to simulate microstructural evolution or solidification. The success of phase field was also relatively recently extended to the area of fracture mechanics. You can see all of these are simulations, by the way. You can see here that very complex cracking phenomena can be captured. So you can see crack branching, nucleation of cracks for secondary sites, coalescences of multiple cracks. So it's quite a compelling tool from that perspective. And we recently have also demonstrated that this phase field paradigm could also be applied to corrosion, to simulate the evolution of the corrosion process. So fracture, corrosion, and many other material degradation challenges have in common that they are interfacial problems. So we really need to be able to simulate how this interface evolves, and therefore phase field has been a game changer for us because it allows us to explicitly simulate what is happening, so to say. So let me tell you a little bit of how we have combined these two ideas to tackle these problems. And at this point, I should say that in several of these problems, we're also doing experiments to understand these material degradation challenges. But of course, today, for the sake of time, I'm going to focus only on our modeling methods. And in particular, I'm going to start first with the hydrogen embrittlement problem. So hydrogen embrittlement is actually quite an old problem, but it has regained quite a lot of interest in recent years. And I think the main reason for it is the important role that hydrogen is going to play in the energy transition. So we know that hydrogen has the potential to decarbonize many applications and sectors, including some that are particularly difficult to decarbonize, such as steel making or aviation. And the key thing for me is that this needs to happen very fast. So there's an urgent push to urgently deploy a hydrogen energy infrastructure. So Airbus is saying that they're hoping to have hydrogen fuel airplanes in the air by 2035. The European Union is saying that they're hoping to have a hydrogen transport infrastructure of 40,000 kilometers of pipelines in 10 years from now. So things need to happen pretty fast. And the problem with hydrogen is that it has a dark side. So hydrogen can very significantly degrade metallic materials. And we know this since almost 150 years ago. So this is a paper from Johnson written in the Proceedings of the Royal Society back in 1875. And you can see that he speaks about some remarkable and extraordinary decrease in toughness and breaking strain in iron and steel in the presence of hydrogen. And in those days, you will very rarely see words such as extraordinary or remarkable in scientific papers. But the way the hydrogen interacts with metals is indeed quite remarkable and extraordinary. So one of these effects, for example, is how hydrogen significantly reduces the ductility of metals. You can see here, this is a stress strain curve, so in the actual tensile test, and you can see that if I introduce hydrogen into my samples, by, for example, exposing them to hydrogen gas, then you see that you get a very significant reduction in the failure strength. Another effect is how hydrogen brings down dramatically the fracture resistance. So you can see here fracture toughness versus hydrogen content, and you can see that for a material that has a fracture toughness of 150 megapascals per meter will fail well below 40 megapascals per meter in the presence of hydrogen. And this is for a low strength steel. And in high strength steels, the reduction in fracture toughness due to hydrogen can be of orders of magnitude. And I think this is a key point to emphasize, the fact that modern high strength steels are particularly susceptible to this hydrogen embrittlement phenomenon. And you can see this here. This is a plot of fracture toughness versus material strength, and this is for a given hydrogen content. So this is representative of seawater. And you can see that these modern high strength steels over here have fracture toughness in the presence of hydrogen that are below 10 megapascals per square meter. So almost as brittle as ceramics. And of course, this is quite important for two reasons. The first one is what this picture is telling us is that hydrogen is effectively compromising decades of metallurgical research. So we have developed high performance materials, but we cannot use them. And the second one is that as we try to use these modern alloys in our cars, in our buildings, in our railways, we're starting to see hydrogen-assisted failures in many applications and sectors where we never heard about before, in otherwise very benign environments. So traditionally, hydrogen was a problem related to aggressive environments, such as those of offshore engineering. But now with the use of these modern steels, we're starting to see failures across all applications and sectors. So this is a newspaper article speaking about hydrogen-assisted failures in the Cheese-Drayton Tower, so not too far away from here. And you can see that it's just the hydrogen coming from the manufacturing or the exposure to humidity that is sufficient to trigger cracking problems under this more susceptible materials. And back to the first topic, right? How are we going to deploy this hydrogen energy infrastructure, given that hydrogen is changing so drastically the mechanical and fracture properties of metals? And it seems that politicians have already made a decision in that regard. It seems that they're going ahead with this hydrogen economy. But of course, this also means that we're going to face some challenges, and we're going to face them pretty soon. So I took this newspaper article here from the Telegraph. I think it was published a week ago, 2 weeks ago, 13th of February. And you can see the National Grid is hoping to have hydrogen transport pipelines by 2025. So in 2 years, they're hoping to have a network of hydrogen transport pipelines. And of course, that's going to bring some challenges. In fact, there's only a few countries in the world that are already starting to establish this hydrogen infrastructure, and they're already starting to see some accidents in there. You can see this explosion that happened in Norway. So there are challenges that are going to come our way. And as you can imagine, it would be very convenient if we had a computational model that we could use for predicting these catastrophic failures. for mapping safe regimes of operation and for determining under which conditions we will not see these kind of accidents. And this is something that is, however, considered a long-standing challenge, and the reason is that hydrogen embrittlement is quite a complicated problem. First of all, it's quite multidisciplinary, but at the same time, it's also complex from the point of view of being multi-scale and from a physical point of view, difficult to understand. We do understand certain things, but there's many other things that we don't fully understand. So we understand that hydrogen atoms coming from gaseous, electrolyte, or water vapor environments will come into the material, they will diffuse through the crystal lattice, and they will accumulate in the fracture process zone where they will interact with the metal in many ways that we don't, as I said before, we don't fully understand. But yeah, we try to make our best to develop this computational framework that will allow us to predict these hydrogen-assisted failures. And to do that, we focus on the three stages, or the three key stages that are involved in hydrogen-assisted failures, and I will discuss each of them. So first we have the first stage, where we have hydrogen uptake. So we need to know for a given gaseous or aqueous electrolyte, how much hydrogen is actually ingressing our metal, right? We need to know how much hydrogen we have on the surface of the metal. Then we need to simulate also the hydrogen transport, so we know that the hydrogen diffuses through the crystal lattice and is also sequestered at certain microstructural sites. So we need to know basically how much hydrogen we have, where and when. And finally, based on this hydrogen accumulation at critical interfaces, we need to be able to predict when hydrogen will trigger the nucleation of cracks and when those cracks will go on to grow and propagate along grain boundaries, for example. So I'm going to discuss each of the steps, starting for the hydrogen uptake and how we simulate those in our finite element models. And regarding the hydrogen uptake, for the case of gaseous hydrogen, at least for steady state conditions, this is relatively well understood. We have closed form solutions like Siebert's law that we can use to understand what is the hydrogen concentration at the surface for a given hydrogen pressure. What is much more challenging is to predict what happens when you have an aqueous electrolyte. Because there basically you have the hydrogen, all the elements of the hydrogen evolution reaction that you need to solve on the surface of the metal. And this is also very sensitive to the electrolyte behavior. So you need to solve the electrochemistry of the electrolyte behavior to be able to predict the hydrogen uptake. But you can do those things. We know the equations that describe these things, and computers are sufficiently powerful these days to predict those things. So I won't get into the details, but what I want to say is that we know what are the reactions that are involved in the hydrogen evolution reaction. We can express the reaction rates as well, so we can express in the mathematical form what is happening at this electrolyte-electrode interface. And you can see here this is dependent on the local pH and the potential. So we need to solve as well the electrochemistry, we need to solve the electrical-mechanical problem. So we can have a system like this one where you have effectively three domains. You have an electrolyte where you solve for as many ionic species as relevant to your problem. You have also you solve for the electric potential over there. Then you have an interface where you're solving for the occupancy of hydrogen atoms in the interface. And then you have a solid metal domain where you're solving the magnetic crack, where you're solving the deformation problem and also for the hydrogen concentration in the bulk of the material. And I won't get into the details, but yeah, there's some equations that describe the reaction rates at the surface. You use Nernst Planck to solve to characterize the electrolytic behavior in the electrolyte, and then you solve the static momentum balance and the hydrogen mass balance on the metal. And this is the kind of results that you get. I'm only showing a representative result. So basically, you have, for example, the distribution of potential or pH within the electrolyte, and you can see how, for example, here the pH changes quite drastically from the bulk to inside of the crack. And then you can see here on the right where you have the lattice hydrogen concentration distribution, so you can predict what is the uptake of hydrogen as a function of time, as a function of the environment, as a function of your material, and as a function of your geometry. So this is just an example, and this is, by the way, for this given applied potential, but you can change all these parameters. You have a virtual platform. If you resolve all these physics of the hydrogen evolution reaction, you have a virtual platform that will let you know how much hydrogen is coming into your metal. And once we know how much hydrogen we have in our metal, then we can move on, and we can look into the hydrogen transport problem. And typically, hydrogen transport within the bulk metal can be described by an extended version of Fick's law. So hydrogen will be driven by gradients of concentration and also gradients of hydrostatic stress. And I like to emphasize this coupling with the mechanical part because I think that is quite important. So, in fact, if you have the steady state equation for the hydrogen transport, it looks something like this, and you can see that you have an exponential term with this hydrostatic stress inside. So it is quite important to properly characterize the hydrostatic stress. And as you know, What this means is that you're going to have much higher hydrogen concentrations ahead of cracks or other stress concentrations. And this is, by the way, the easiest way that one can simulate hydrogen uptake or hydrogen diffusion within the material. In reality, we know that hydrogen atoms not only travel freely through the crystal lattice, they're also sequestered at what we call microstructural traps, like grain boundaries, carbides, locations, and so on. So we have developed, we have implemented numerical models or theoretical models that are based on thermodynamic equilibrium can characterize how the hydrogen distributes itself between the lattice and trap conditions. And for example, very often we're interested in what is the concentration of hydrogen on the grain boundaries, because it could be a weak interface. But with these models, we're able to quantitatively know where your hydrogen is. And once you know where your hydrogen is, then you need to model this embrittlement process. And for that is where we use the phase field model that I showed you before. And one thing that I didn't say before is how does the phase field evolution equation evolve this, right? So how does the phase field evolve? And in the context of fracture, one of the beauties of this method is that you can use it to provide a variational framework for Griffith's energy balance. So those of you familiar with fracture mechanics will remember that Griffith postulated that a crack would grow if the energy stored in the solid was sufficient to overcome the energy required to create tuning surfaces. And you can express that into a variational form. And if you're able to minimize this functional, you can capture how cracks evolve as an exchange between stored energy and fracture energy. However, this is not easy to do because you don't know basically where your crack is, you don't know where your interface is. And here's where the phase field comes to our rescue, because we can use the phase field as a marker, and this will tell us where our interface lies. And you can see that the phase field is a little bit like a damage variable, so it's regularized in this problem, and it goes from 0 in intermittent material points to 1 in fully cracked material points. It's also kind of a non-local damage model. You have a lens filling there, so that gives you mesh objectivity, and it degrades, as you can see here, the stiffness of the solid. And you can get a good overview if you take a look at the balance equations. So in the top, you have the balance of linear momentum with the phase field degrading the stiffness of the solid. And here is the additional differential equation that you solve for the phase field, which is effectively a competition between your fracture energy and the energy stored in the solid, which is increasing with your mechanical strain. And just by solving this additional differential equation, you can capture very complicated cracking patterns on the region of an element mesh and in a very robust fashion. So all the results that I'm about to show have been computed in a standard quasi-Newton, in a standard Newton-Raphson approach, so Buffer-Euler without any convergence issues. And you can see here, for example, crack branching. This is happening because I'm applying a dynamic load, so there's some crack wave interactions, and you can see the complicated crack branching can be easily captured just by solving this additional differential equation. And yeah, this slide, I hope that convince you of the capabilities of these kind of methods, because they're not only useful in being able to capture very complex cracking phenomena, but they're also useful in providing a good agreement with experiments, because they're based on this thermodynamics of fractures. So this, as you can see, provides a very good agreement with experiments. And I have incorporated a few examples here for the several groups, including some of the nice work that Wei Tan has done with phase field methods in trying to bring insight into the micromechanical behavior of composite materials, which I think show also quite nicely the capabilities of these methods. So back to the hydrogen problem. Essentially, we have three equations that we're going to solve in the bulk method. So once we know what is the hydrogen in the surface, that's a boundary condition for the hydrogen concentration. And then we need to figure out where the hydrogen is and when is it going to cause cracking. So I'm emphasizing the couplings here, but of course the most important coupling that I'm missing is the fact that hydrogen is affecting the damage process. And qualitatively, we know very well how to define this coupling, so we just need to make our fracture energy dependent on the hydrogen concentration. But the question is, how do you do that quantitatively? And one way that you could do it is in a phenomenological way. So you could run experiments and measure fracture toughness versus hydrogen concentration and implement this function for that specific material. And this is one of the ways that some of our industrial partners decide to go ahead. However, I didn't like to propose a model that requires so much experimental calibration. Ideally, I wanted to propose a mechanistic model that had no fitting parameters whatsoever. And so I'll tell you a little bit of how I came up with this, what I think is the ideal fracture energy degradation function in the presence of hydrogen. But I should emphasize at this point that this framework is universal, that whether you agree with me or not in the interpretation of the mechanisms is not important. You can always define your hydrogen degradation function as a function of, whatever micromechanical or macromechanical variable that you think is interesting. It could be hydrogen trapping dislocation density, whatever you believe is relevant. But anyway, this is what I believe is relevant. So, of course, the key question when trying to come up with a mechanistic interpretation is, How can it be that a metal that fails in the absence of hydrogen in such a ductile manner with microvolt cracking mechanisms fails in such a brittle fashion in the presence of hydrogen? You can see here with these cracks originating on the grain boundaries. And in my opinion, there's three key ingredients to understand this. The first one is that when you do atomistic calculations, this is DFT for nickel, several types of grain boundary, what you see is that hydrogen very significantly reduces the fracture energy. So you can see here that when you have full hydrogen occupancy, so this is the occupancy of the grain boundary, when you're going all the way to 1, you get a 40% reduction in the fracture energy. The second thing to consider is that, okay, so this is the first ingredient, and this is quite important. However, you may wonder how much hydrogen is in our grain boundaries, right? Because if somewhere we are in this side of the graph, then we're not going to have a lot of hydrogen, and the reduction is going to be small. So the next question is, how much hydrogen do we have in our grain boundaries? And the answer to that comes from the trapping thermodynamics. So you can use Oriani's equilibrium to express the trap binding energy with the hydrogen lattice concentration and the trap occupancy. And the trap binding energy is a material property that we can measure in our labs, and that tells us how energetically favorable it is for the hydrogen to go to that particular microstructural feature. And grain boundaries are strong traps. We measure in our labs something on the order of minus 40 kilojoules per mole. So you can see that with very little hydrogen contents, as little as 1 part per million, our grain boundaries are effectively going to be almost full. So it is very energetically favorable for the hydrogen to sit in grain boundaries. And when this is the case, we know from our atomistic calculations, we're going to have a very significant reduction in fracture energy and bonding strength. And when you put all these things together and you combine this with some microscale plasticity models that I don't have time to discuss, what you see is that in the absence of hydrogen, your stresses are not high enough to reach the cleavage strength or the grain boundary strength. But the moment you bring the hydrogen in, you lower your cleavage strength, and then these two lines cross, and you have a story. You have a model that, without any fitting parameters, can capture this transition from ductile to brittle failure. This comes very easily and naturally in a quantitative fashion in the phase field model, because as you can see here, we are solving for the diffusion problem, so we know how much hydrogen we have in our lattice, where and when, in which regions of the component. We can then apply those trapping thermodynamics to determine what is the occupancy in that interface that we're interested in, like a grain boundary. And then we can go to these atomistic calculations and quantitatively predict what is the degradation in fracture energy. And we can do that. This atomistic calculation you only need to run once in your lifetime offline, and that's all. So let me show you some representative results with this framework. And before I do so, let me also emphasize that we're not only interested in the nucleation of cracks, we're also interested in some critical crack growth. So we want to model, as you can see in the slide, how whenever a crack is propagating, if our sample is exposed to a hydrogen-containing environment, the environment is going to follow readily. So if you have, for example, a pipeline in the middle of the sea, the moment the crack propagates, these newly created crack surfaces are going to be immediately exposed to the source of hydrogen that is, in this case, the sea. And you can see that we can capture that easily with a penalty approach, and there's many other approaches that we can use. But let me show you some results. So these are R curves, crack growth resistant curves. So the y-axis is a measure of the applied load away, or the crack tip stress condition, and this is the crack extension. And you can see that we get what we expect from the experiment. So as you increase the hydrogen concentration, you lower the crack growth resistance. Another interesting effect is the sensitivity to the loading rate. So again, we see what you see in the experiments. If you load very fast, there's not enough time for the hydrogen to accumulate in the fracture region. As a result, you gain some fracture resistance. But if you load very slowly, then you leave enough time for the hydrogen to accumulate in these critical areas, and you reduce your fracture resistance. And we can also get quantitative agreement with the experiment. So this is some pre-charged steel bars, and we're measuring the notch tensile strength versus the hydrogen concentration. And as you can see, the model seems to agree very well with the experiments. And this is another set of more interesting experiments. So these are notch samples that were immersed in a seawater bath. This was done in Norway, at Sintef. And then they loaded each sample at a constant load, but all of them at a different load. And what they were hoping is that one of the samples was subjected to a stress level that was small enough that you will not see any embrittlement. However, as you can see here, the symbols are experiments. They all fail relatively early for engineering purposes. But we can use our model not only to reproduce experiments and gain confidence in our predictions, but also to run virtual experiments over very large timescales. This is the key point. So we can determine what is this critical threshold below which we won't see any hydrogen embrittlement. And in general, we can model anything we want. So this is a classic standardized test from the STM standard, where you look into the failure of a screw that is exposed to an abrasive environment. So you have a metallic screw inside of a concrete plate, and you can see here that we can capture the full rupture of the screw. And we can also more excitingly couple this with inspections. So you can create sort of a digital twin of critical infrastructure. So here you see, this is a 12-kilometer pipeline that was characterized using AI rendering by Nicola Rosa and co-workers. And all of these red dots here are pit corrosion defects. So the pipeline was full of these defects. And we decided not to model 12 kilometers of pipeline, but to model a critical section of 3 meters. And there we introduce hundreds, there's more than 100 of those defects in there. And we can, because we're solving for the phase hill as a degree of freedom, it's very easy for us to introduce as an initial condition those damaged regions. And then we can load our pipeline to in-service conditions. And just to see here how we can just apply the in-service conditions. This is a riser pipeline, I think. And you can see here how the defects eventually start growing. They eventually merge with neighboring defects, and eventually you get this complete failure of the pipe, which you can see here more extended version. So the key takeaway at this point is that we do have a virtual platform, we do have a computational tool that allows us to predict quantitatively and qualitatively hydrogen-assisted failures as a function of the material properties, the environment, and the loading conditions. And we recently extended this to fatigue, where you have basically another fatigue degradation function that accumulates with the number of cycles. And you can see that we can predict virtual SN curves, and we get a good agreement with experiments. And also we can predict, as a natural outcome of the model, the Paris load behavior, also as a function of the hydrogen concentration, and also virtual SN curves for any arbitrary loading history or any arbitrary geometry. So here you can see a geometry with a notch. So these cycle-by-cycle calculations are quite powerful in that sense, because they allow you to deliver fatigue predictions for any arbitrary choice of loading history and environment, of course. Okay, so that's all in relation to the hydrogen. That takes me to the second part of my talk, which is related to the lithium-ion battery degradation. And I don't think that this needs a lot of motivation. Lithium-ion batteries are part of our daily lives. But of course, we want cars, electric cars that can reach longer distances. We want more durable batteries in our phones, in our laptops. So we're interested in unraveling some of the material degradation mechanisms that are compromising the durability of these lithium-ion batteries. And what is happening here basically is that whenever you charge, you have lithium ions going from the cathode to the anode, and from the anode to the cathode when you discharge. And that transport of lithium ions, this lithiation, what happens is that it's intercalating into these storage particles, and it's causing mechanical strains and volumetric changes. And this cyclic shrinking and swelling of these storage particles is causing the nucleation and growth of cracks in those particles. And this is one of the mechanisms that is degrading battery performance. So what we try to do is to use this kind of multi-physics phase field fracture models to try to map under which conditions of charging and charging and material properties we will see these kind of cracks appearing. And we wanted to do so also for fatigue, because a number of people have developed phase field models for electroparticle cracking, but they were only looking at one charge cycle, and we want to do it for multiple. This is, of course, a cyclic problem, so we wanted to do it for multiple cycles. And one thing that I want to say is that when you look at the equations, they're actually not very different from the hydrogen problem. So again, you're solving a coupled deformation, diffusion, damage problem, and there's essentially two differences. One is that our fracture energy does not depend too much on the lithium content. There are some mechanistic calculations by the group of Bill Corting where they see some effect, but it's not a very significant effect, nothing to do with hydrogen, where the effect is massive. And the other thing is that this partial molar volume is one order of magnitude larger, and as a result of that, you have these chemical strains that are negligible in hydrogen, but they're very significant here due to this lithium intercalation process. So these chemical strains is what is going to cause this mechanical damage. So again, as I said, our plan was to extend this to fatigue, not only look at the half cycles, and we model not only idealized particles subjected to cyclic loading, but also realistic particles as you can extract from HCT imaging. And yeah, these are some representative results. At the end of the day, what you have is, again, a virtual platform whereby you can change the loading conditions, you can change the material properties, you can change the particle radius, you can change anything that you want and test it and see what is the impact on the fatigue behavior. For example, you can see here that we can determine what is the particle radius and the C rate thresholds below which we will not see any fatigue cracking for 300 cycles, which is a sensible estimate for this batteries in the context of electric vehicles. But we have also taken this one step further. So this is work together with Alan Boyce and Paul Schering at UCL. And we have decided to go one step further and model the entire electrode. And you can see here that this also builds on the fantastic imaging capabilities that they have there at UCL. So we're able to characterize the entire electrode, and therefore we can not only model electroparticles, but we can also model other phases like pores and carbon binders, and we can see the role that these multiple phases play. And you can see here, this is a 2D segmentation image, so you can see here the image that you get from the XCT, how the segmentation process goes, and then how in your finite element problem, you're predicting for a realistic microstructure, what is the propagation of that. Here are some representative 3D results. Again, here, for example, we were changing the thickness of the electrode, and we can see that it's a very heterogeneous response, both from the electrochemical and the fracture behavior point of view. So again, it's the same takeaway. This sort of multi-physics, physically based phase field models allow you to simulate what is happening in reality, and you can easily tune things and change material properties. You can change charging conditions. You can change voltage windows. You can change things and see what is the impact on the structural integrity perspective. And we have also taken this one step further and look into the microstructure. And you can see here again, exploiting these amazing imaging capabilities that our colleagues at UCL have. And you can see here that we can capture very nicely, in this case, we're modeling intergranular crack in the particles, as you can see. And one last item on the battery part. This is related to solid-state batteries. So solid-state batteries are arguably the next big breakthrough in battery technology. So if you're able to replace a liquid electrolyte by a solid one, you're not only gaining in safety, but in principle, you could be gaining an order of magnitude increase in capacity. The problem that is basically hindering the commercialization of these solid-state batteries is the fact that you have a lot of interfacial problems on the interface between the lithium metal anode and the solid electrolyte. And particularly problematic are these dendrites, which are kind of needle-like, they're kind of needle-like filaments that initiate at the lithium anode and then go all the way to propagate to the cathode and therefore short-circuit the battery. And you can see it very nicely here. These are some very nice experiments from Peter Bruce group in Oxford. So you can see that initially you have the lithium metal and the solid electrolyte, and then every time you discharge the battery, you have stripping. So you are removing lithium from the anode, and therefore you have these voids that are originating there in the lithium anode. And every time you charge, you have plating, so you're depositing lithium, and therefore you're shrinking these voids, and you are often isolating them from the environment. And being able to capture this voiding process precisely is quite important, because near the edge of those voids, you have what we call current hotspots, which are regions of localized current or very high currents, where plating is exacerbated and dendrites form and grow. And since that it's quite difficult to stop these dendrites from, once to nucleate a dendrite, it's very difficult to stop them. So we're trying to focus our efforts in understanding under which conditions you form those dendrites. And for that, it is essential that we understand this voiding process. So we developed a theoretical and computational model to understand this. And this model has multiple ingredients. One is, of course, the interface reaction. So whenever you're doing stripping, you are removing lithium atoms, so that you can capture through a boundary condition. Whenever you have plating, you are depositing lithium atoms in your material. So again, we can use this through a boundary condition. You also have vacancies or substitutional and surface lithium diffusion within the bulk. And this we can capture by solving some sort of transport equation for the lithium coverage. And then, of course, we have the voiding process, which is essentially vacancy nucleation and annihilation. And this is quite important, as I said before, because this is what is going to generate those current hotspots. And this is nothing but an interface that is evolving. So this is a perfect problem, again, for phase field modeling. So again, multi-physics and phase field, because we have an interface that is evolving, in this case, in the voids. And of course, we have quite a lot of mechanics in here. So you have a lot of lattice distortion. And more importantly, the main hypothesis nowadays in the solid-state battery community is that you can suppress those voids by applying a mechanical pressure through creep and viscoplasticity. So we need to capture down those viscoplasticity effects and have a viscoplastic number. And this is the kind of the problem that we solve. So again, a coupled electro-chemo-mechanical problem. So we're solving the electro-chemo-mechanical problem both in the anode and the electrolyte. So we can naturally see those hotspots that I mentioned before. And you can see here that these are basically the governing equations. So a phase field equation for the voids, a transport equation, and then a mechanical problem and the electric problem. And just to show you some representative results. So this is what you're seeing here, stripping of a single void. And you can see that basically we see what we expect from the experiment. So here you're seeing the face field, so you're seeing the void growing, enlarging on the vertical direction, which is exactly what we saw in those experiments of Peter. And you can see that naturally the model is able to capture those hotspots, those current hotspots in the electrolyte. You can see these regions where the current is localized in the void. And if we do plating, again, we observe the same as we see in the experiments. So again, you can see that the void is closing during the plating cycle, and eventually even detaches from the surface, as we saw in those SEM images from the Oxford group. And of course, we can model more complicated or realistic scenarios where we have maybe multiple voids, you're applying a pressure, so those voids are kind of shrinking a little bit, they're also coalescing with neighboring voids, and you're losing those hotspots, you are eventually killing those voids at some point, and you can do over, of course, multiple cycles of charge and discharge. So again, this combination of multi-physics and phase field modeling gives you this virtual mechanistic platform that you can use to change the cell geometry, to change the applied pressure, to change the initial distribution of voids, to have basically to do virtual experiments to figure out what are safe regimes of operation and what are suitable interface and cell configurations that will enable this solid-state battery reactor. And we've also looked into anode-free solid-state batteries, and this is work together in collaboration with Matt McDowell at Georgia Tech. So he's doing very nice work on the anode-free batteries and then very nice characterization work and imaging work. And we use our model to confirm what this experimentalists hypothesized, which was the fact that this uneven plating and scraping that you get in anode-free solid-state batteries was responsible for these degradation mechanisms that we're observing, for the short circuit, early short circuit of these solid-state batteries. And this is what we see with our model as well. You can see that this protuberances easily lead, or this non-uniform plating easily leads to this nucleation of voids and this high localized currents there. So, last part of the talk, we're going to localize corrosion. And again, this doesn't need a lot of motivation. You all know that corrosion is a massive problem for society, it has a huge economic cost. And more importantly, has been a long-standing challenge to predict for scientists, both scientists and engineers. And why is corrosion so challenging to predict or to simulate? Well, there's multiple reasons, but again, all comes back to my main point, right? It's a complicated interfacial problem, and it's a very strongly coupled multi-physics problem. So if you think of, for example, the corrosion fatigue of offshore wind turbines, which is their limiting design criteria, you can see that the process is something like this. So you nucleate some pits over there, then those pits grow, and eventually they transform into cracks, the fatigue cracks that go and grow all the way until the failure of the monopile. And how these pits grow, how fast they grow, and when they turn into cracks, is very sensitive to their shape and to the deformation and chemical problems. And at the same time, the deformation and chemical problems are very sensitive to the shape of the pit. So you know that if a pit is very sharp, of course, you have a higher stress concentrator, and if the pit is very sharp, also the local chemistry is going to be much more different than the bulk chemistry. So everything is very strongly coupled. If you really want to know how fast that pit is growing, you need to know exactly the morphology of that pit, and then resolve the electrochemistry inside of that pit and the mechanics next to that pit and the corrosion process. So again, this seems like a very suitable kind of problem for phase field. So I'm not going to get into the details for the sake of time, but again, the idea is that you use the phase field. In this case, the phase field basically tells you whether you are in the aqueous electrolyte, like the seawater, or whether you are in the metal. So it's describing how the metal is dissolving as part of the corrosion process. And I'm not going to get into the details of the phase field equation. It's more based on phase field solidification models, like KKS model, and not that much on the fractal ones. But at the end of the day, basically, you end up with, in the simplest form, two equations. One for short-range reactions or short-range interactions, so material dissolution, the phase field describing how you're losing material, and then one for the long-range interaction, which is basically the diffusion of metal ions far away from the interface. And just to show you some representative examples, you can see that we can predict pitting and also stress corrosion cracking very nicely with this method. And we've looked into a number of representative case studies. This is a classic benchmark where you have basically 1D corrosion. And here there's an analytical solution for the case of diffusion metal corrosion. And this is basically the kind of results that you expect. So you can see with time how the corrosion front is evolving, and you can see the distribution of metal ions away from the corrosion front. And basically, this is a good example to validate the model with analytical solutions for the case of diffusion metal corrosion, because this is a 1D example, and also to show that the model can naturally capture the interplay between activation control corrosion and diffusion control corrosion. So the model depends on only two parameters, essentially. This mobility coefficient here, which controls, is quantitatively related to the corrosion current rate, and the diffusion coefficient of metal ions, which you can, again, measure experimentally. So you can have here, you can measure this guy experimentally. And depending on the magnitude of these values, you can get either this linear behavior of activation control corrosion, or eventually this parabolic behavior of diffusion control corrosion. And then, of course, in the diffusion control corrosion regime, if you change the diffusivity, you get different behavior. Other examples where we show good equilibrium with experiments. And basically what we have done ourselves is to try to introduce more mechanics into these models. So we know that mechanical fields can enhance corrosion kinetics. This is discussed by Goodman already almost 20 years ago. And we can do it, we can introduce easily that into the phase field because this mobility coefficient can be quantitatively related to the current density. So we can make our mobility coefficient dependent on mechanical fields. And then we can run some virtual experiments like this one to see whether we are able to capture the sensitivity to the mechanical fields. And you can see here some experimental results, so comparison with experiments. You can see that we are able to capture very well, we get a very good agreement with experiments conducted at two very different apply loads. And you can see that we also get a very good agreement in terms of the morphology of the defect of the peak, right? So these two images are on the same scale. And you can see that we only focus on one peak, but we could have modeled those other peaks, and you can see that we get a very good. Another factor that we have to incorporate, of course, is this film resolution repassivation mechanism. So typically, many materials like stainless steel will develop a passive film that will protect them from corrosion. But what you have is that if your mechanical loads are high enough, you will eventually rupture that film, and that's when you get this localized corrosion. Until it repassivates again. So it's a competition between crack tip straining kinetics and this repassivation kinetics. And we can capture that again easily into our model, so we can capture how we have this film that doesn't allow us to protect us, and we can see we can have a parameter that we can tune to capture this interplay between the repassivation process and the crack tip straining. And just to show you that, of course, if we're using phase field, we can capture very complex pitting conditions, and we can do this in 2D, we can do this in 3D. And I'm quite excited about this area. I think that we're going to see a revolution in corrosion modeling, similar to what we have seen in microstructural evolution or fracture, because people will typically tell you that corrosion is very difficult to model with computers. They would say that it is a too complicated process, there's too many things happening at the same time, in addition to this situation where you need to accurately track this cracking morphology or this corrosion morphology. But the thing is that we know we have equations that describe each of those physical phenomena, and now we have a tool finally that allows us to couple all of those and to track the corrosion from. So we can easily incorporate the effect of the chemistry. We can easily couple that with the hydrogen embrittlement models that we've shown you before, and we have done that in the past. You can also model intergranular corrosion. So there's many things that you can do, and we look into some of these things. For example, the role of the microstructure. So the microstructure will play a role because you have some anisotropy not only in the mechanical properties but also in the corrosion behavior. We have seen this experimentally, and we can easily incorporate that into our model by defining a new mobility coefficient. And you can see here some examples of this is an isotropic case, and this is a case where we introduce a microstructure, and you can see how you have a different behavior whether you have the microstructure, you take into account the microstructure. Now, we can also incorporate more complicated microstructures where maybe you have secondary particles in there that do not corrode, and as you can see, the model is easily able to capture those things. And of course, we can also incorporate electrochemistry. So we can solve for as many ionic species as we can, and yeah, some of these models have, I don't know, 15 degrees of freedom, but nowadays computers are able to handle those things. And so we can have as many ionic species as we can, and then we can capture the effect of the solvent concentration, of applied potential, and so on and so forth. And last but not least, this is my last slide, we have also looked into biocorrosion, so the degradation of magnesium in simulated body fluid. And this is quite important for scaffolds that are trying to do scaffolds of biodegradable materials, such as when the bone heals, there's no need for a second surgery operation to remove that component. And we can use exactly the same idea, and we're able to capture a very good renewable experiments. Okay, so I think I reached the end of my time, just on time. So I will just finalize with two kind of high-level conclusions. The first one is that I think that the combination, so many of these material degradation challenges are challenging to simulate from a physical point of view because of two reasons. One is they're very strongly coupled physical phenomena, so you need to simulate a lot of things at the same time. The other one is that you have a moving interface, there are interfacial problems, and you need to be able to resolve that interface if you want to get accurate predictions. So I think that the combination of phasing modeling and multiphysics modeling gives you these capabilities, and allows you to finally explicitly resolve those physical processes that are happening in those materials. And then you can be predictive, and then you can change things here and there and see what is the outcome of that. And yeah, finally, I will just say that I hope to have convinced you that the coupling of phase field methods and multi-physics modeling has allowed us to predict the failure of materials exposed to hydrogen. And this is, of course, critical for the energy transition. And our industrial partners are using these models to design pressure vessels for hydrogen storage and answer questions related, for example, to the use of gas pipelines to transport hydrogen, or natural gas pipelines to transport hydrogen. Also related to the degradation of battery materials, looking at electroparticle cracking, both at the particle scale and at the electrode scale, and both at the continuum kind of macroscopic scale, and also resolving the microstructure and looking into microscopic cracking mechanisms, but also looking into other interfacial problems such as voiding solid-state batteries, which could be key to unravel this solid-state battery breakthrough. And finally, corrosion in aggressive environments. We know that corrosion is a long-standing problem for scientists and engineers that has important implications in society. And it's a problem where a lot of very good experimental research has been done in the past 50 or 70 years. So we can leverage on that nice experimental corrosion research, and we can develop these computational tools that will be able to predict everything, all the physical processes that are happening in there. And you can capture the influence of the electrochemistry, the microstructure, and anything else. That's all. I would just like to say that all my codes are openly shared. We typically use Abacus, but we also use our own codes in MATLAB or C++ or Phoenix or Console lately quite a lot as well. And all my codes are available on my website, so you can download them and reproduce the results that I've shown you today and do many other stuff. And of course, thanks a lot to you for your patience, and also to our sponsors for supporting our research. Thank you so much.